Hi, guys. Okay, so let's finish the exercise problems from chapter 7 in the Libre text, Introductory Chemistry by Tro. So first of all, it's very important. Once again, I would like to emphasize that you really need to recognize the polyatomic ions, the symbols of the elements, and you should know the charges. And then based on that, you're going to determine the solubility of the ionic compounds. Okay, so that's very important. So make sure you memorize that. Next thing is, we are going to now look at these questions, the gas evolution reactions, okay, where the intermediates are formed and these are unstable. So let's look at these. So here we have sodium bicarbonate. So bicarbonate is a polyatomic ion. And then we have the chloride, and then we have hydrogen, and we have sodium. So once again, outer, inner, sodium is going to combine with chlorine, and the bicarbonate portion is going to combine with hydrogen. So what is it going to give you? It will give you NaCl, and it will give you H2CO3, right? So just simple combination. But H2CO3 is unstable. So what is going to happen? It will break up into two parts. And what are those two parts? Those two parts are, it will break up, this piece is going to break up into water and carbon dioxide. So water is a liquid and carbon dioxide is a gas. So you will see here bubbling in this reaction because of that. The fizzing or bubbling occurs because of the evolution of carbon dioxide. And that is due to the unstable. This is called a carbonic acid. Carbonic acid, and carbonic acid is unstable. All right, so this is one piece. Next, let's look at another situation where a gas is formed. Now, here we will see, in this case, we will see the potassium, once again, outer, inner. So potassium is going to combine with chlorine, and hydrogen combines with sulfur. Okay, so here you will see the gas evolution, maybe not unstable, but you're going to see the formation of KCl, and another gas is H2S, hydrogen sulfide. Okay, so obviously this is not balanced. The first one is balanced. If you can see the first one, two hydrogens, and two hydrogens. And then carbon dioxide was, here is the carbon dioxide is 3 oxygens. So 2 plus 1 is 3 oxygens, and 3 oxygens from here. Okay, so that balances. So in this case, it was balanced. But in this case, we have 2 potassiums and we have only 1 potassium. So we need to balance the potassium. So what are we going to do? If we add 2 here, so that balances the potassium. But it messes up with the chlorine. So you're going to put 2 in this side. So that 2 applies to hydrogen and the 2 applies to the chlorine also. So in this case, we have 2 hydrogens. Let me color code. So we have 2 hydrogens. Sorry, another color. 2 hydrogens here, 2 hydrogens here. 1 sulfur here, 1 sulfur here. And then we have 1 chlorine, or rather 2 chlorines, and so here's the 2 chloride ions and 2 chloride ions. And then the potassium is balanced this way. Okay, so this is a balanced reaction. And here we see, but this is hydrogen sulfide, and hydrogen sulfide is a gas. So here also we are going to see fizzing or bubbling, in this case also, or fumes, so those things you will see. And this has a very characteristic smell, like rotten eggs. So this smells like rotten eggs smell. Okay, fizzing or bubbling. Okay, so KCl is soluble in water. All chlorides are soluble except, the Castro bar, which is the calcium, strontium, and barium, and then lead in +2 state, mercury and silver. So those are not silver in +1 state. Those are not soluble in water, but all the other group 1A elements, ammonium and all the others are soluble in water. So chloride is soluble. HCl is an acid. This is soluble in water, so it's AQ, and potassium sulfide. So sulfides are insoluble, but when sulfur is attached to a group 1A element, such as sodium, so this is soluble, so this is going to be aqueous. Okay. Sodium bicarbonate, again, group sodium is group 1A, aqueous, soluble in water. HCl, acids, all soluble in water. Sodium chloride, salt, soluble in water, group 1A, okay? And sodium bicarbonate, carbonic acid, all carbonic acids are soluble in water, but they dissociate, give you carbon dioxide, which is insoluble in water, so it fizzes out. All right, next is potassium. Potassium sulfide and HCl. So same story here. What is happening is potassium is going to connect with the chlorine and hydrogen with the sulfide ion. So what is giving you? So here we see, because this is potassium group 1A, this is soluble in water, HCl soluble in water. It's very important to determine that. Next is we are getting KCl, and here we will have H2SO3. Now this is the sulfurous acid. Okay, so this sulfurous acid is unstable. Sulfurous acid. Remember, sulfuric acid is H2SO4, but sulfurous is H2SO3. All right, now here what do we see? This is, in this case, we see, let's balance this first. So 2 potassiums, did we balance this? 2 hydrogens, 2 chlorines, 2 potassiums, and 1 sulfide ion. Okay, so what are we seeing here? H2CO3 is unstable, so it is going to break up. And again, it is going to form the H2O, which is a liquid, and sulfur dioxide gas is released. So once again, for all, all these reactions, gas evolution reactions, you're going to see bubbling and fizzing. So, but you see this is unstable. This thing, even though it is aqueous, soluble in water, but it is going to break up into 2, parts, water and sulfur dioxide, which are like water is liquid and sulfur dioxide is a gas which will be released out of this reaction. Now let's look at in this case of KOH. Now KOH once again, and ammonium chloride. Potassium combines with the chlorine, gives you potassium chloride, and ammonium combines with the OH. And so what is it giving you here? This is giving you KCl plus NH4OH. Now NH4OH is a hydroxide. So this is also unstable. So this is ammonium hydroxide. Okay, ammonium hydroxide. And this is also unstable. So what is it going to do? It is going to release the ammonia. NH3, it gives you NH3 as a gas, okay, and water. Okay, so the number of hydrogen ions and the number of OH ions is the number of hydrogen ions, oxygen, and the hydrogen. So look at the hydrogen ions, 4 plus 1, 5. 2 plus 3 is 5. So that's same. And we have the oxygen is just 1 oxygen, and we have 1 nitrogen. So 1 nitrogen here and 1 nitrogen here. So all this is the same, the number of, but it splits up into its 2 parts, and this is the gaseous part and the liquid part. Okay, liquid is water, gaseous is ammonia. So as usual, this is all balanced, I believe. Potassium is 1, and then OH, oxygen is 1, hydrogen is 1, ammonium is 1. So all this is balanced. Okay, so the only thing is you have to keep this in mind is the unstable one. So ammonium hydroxide, unstable, ammonium hydroxide, unstable, sulfurous acid, unstable, and carbonic acid are unstable. And the H2S gas is oh, sorry, why did I write this? This should be a gas. Sorry about that. This is a gas. Okay. All right, next is assigning oxidation numbers. Now here, there are rules regarding the oxidation numbers, okay, and which are already given in your handout. So we are going to just move forward with that in the handout. Just a minute, let me see if I can show you where they are in the handout. So hold on. Okay, so in your handout, you will see this this table, and these rules for the oxidation numbers are given. So this table is talking about the oxidation and the reduction. Basically, increase in the positive charges, or when you move the oxidation numbers, or the oxidation numbers are moved from a negative to 0 to positive side, it is going to be oxidation. So loss of electrons is oxidation. And also the increase in the positive charges is oxidation. Opposite is the reduction. Decrease in the positive charges is a reduction, or in other words, increase in the negative charges is reduction. Okay, so as you can see, you are increasing in the negative charge. Going from a 0 negative charge to a negative charge is going towards the negative charge is reduction. But moving from a negative charge to a neutral state, like that is 0 state, is oxidation. Similarly, if you look at this here, going from a negative and going from a neutral state to a positive state is oxidation, but going from a positive state to a neutral state is reduction. Same is the case here. Increase in the positive charges is oxidation, but decrease in the positive charges is reduction. And then here is when the negative charges are reduced, or there's a reduction, or the less number of negative charges means oxidation. But if there is an increase in the negative charges on the opposite end, reduction. Okay, so this is given to you. It's all about the movement of electrons. Oxidation reduction, as we discussed in the lecture, is the bookkeeping of electrons, like where are the electrons at one particular point of time, what are they doing, how many electrons are being lost or gained, and so forth. So these are the rules regarding the oxidation numbers. So free state means an uncombined state, oxidation number 0, which means that the electrons are not moving. The electrons are still with that particular atom. So for example, copper, iron, silver, like in this state, free state, that is the oxidation number is 0, means that the electrons have moved. So typically oxidation numbers are similar to the charges, right? But if they are like but something else is also there. Now diatomic molecules, because those electrons are bound, they are not available. So all the diatomic molecules like oxygen, hydrogen, chlorine, nitrogen, 0 oxidation number. Okay, then the oxidation number of hydrogen is always +1, except for the metal hydrides where it is -1. Oxidation number of oxygen is always -2, except for oxygen in the peroxides where it is -1. Then all the group 1A, 2A, their charges are, the oxidation number is equal to their charges. Now here's something that I did not write out, is that, see, think in mind, D block elements, many of them have more than one type of positive charges. Similarly, the post-transition, so transition elements and the post-transition elements, they have oxidation, they have more than one type of positive charges. So similarly, their oxidation numbers are also going to be more than one type, right? Depending upon what charge state they are in. So which oxidation number or which charge is being applied in one particular molecule, that we determine by the calculations. So we will just look into that. So all the group 7A, all 7A is -1, but there are exceptions. It can be more than that. It can be -3, -2, but sorry, it can be -3, -5, and -7 also, or positive also, depending where they are. So we are going to look at those also. Then the oxidation, the main thing here is the total charge on the atoms, of all the atoms in an ion is equal to its negative charge, but for a neutral molecule, it is equal to 0. So now let's look at these type of questions, assigning the oxidation numbers for, let's say phosphorus. So hydrogen, the oxidation number is always, so I'm writing the oxidation numbers in the brackets while doing the calculation. So for phosphorus, we are going to find, so phosphorus, let's consider phosphorus to be X. So here, 3 hydrogens, each having +1 charge. So this is for hydrogen, plus for the phosphorus is X, right? Plus 4 into -2, okay, for the oxygen. And since this is a neutral molecule, oxidation number is, for all the sum total of all the oxidation numbers is 0. So let me just color code this. This is hydrogen. So this is the hydrogen. This is oxygen. So this is for the oxygen. Okay. And then for the phosphorus is this. This one is the phosphorus. Okay. So we see here the oxidation numbers are in oxidation. So I have to write it because one of the students were like, what is this +1? And what is this? So these are the oxidation numbers. Okay. And these are the atoms. This is the 3 hydrogens and this is the 4 oxygens. And this one is for the phosphorus. All right. So I placed it because of the lack of space. I'm not going to write down the details much now. Here we will have 3 times +1 is +3 plus x. Now 4 times -2 is -8. Okay. So, and this whole thing is 0. So plus x minus 8 is equal to 0. So what do we get here? X plus, so x minus 5 minus 8 plus 5 plus 3 is equal to x minus 5 is equal to 0. So here when you do the math, x is equal to +5. So here the oxidation number of phosphorus is equal to +5. All right. Now, so +5. Okay. Now, magnesium is in group 2A. Oxygen is always going to be -2 oxidation number. Okay, so therefore magnesium 2A is +2 and oxygen is -2 oxidation number. So that's one piece. Similarly, chlorine, it is a diatomic. So for the diatomics, the oxidation numbers is equal to 0. All right, then comes the calcium nitrate. So for calcium, so calcium is group 2A. So calcium is group 2A. So the charge is +2. Okay, so for nitrogen, we are going to determine, because nitrogen, it can vary. Oxygen is equal to -2 oxidation number. Okay, so now let's set up this problem. Here we have, calcium is +2 and it's only 1, right? +2 plus for nitrogen. So this would be 2x, right? This 2 applies to nitrogen and this 2 applies to oxygen. So what do we have here? +2x plus for nitrogen, and then 2 3s are 6. 6 oxygens and the charge is -2. And this is a neutral molecule, so the sum total is 0. Got it? Oxygen is +2 oxidation number. There are 2 nitrogens, so it becomes 2x, and then 2 3s are 6 oxygens, and the charge on the oxygen is -2, and so that is equal to 0. So let's do this now. So this is -12, this is 2x, and this is +2. So this becomes 2x -10. Okay, and then when you solve it, then this becomes is equal to 0. So this becomes, so 2x is equal to +10, and then x is equal to 10 divided by 2, and that becomes +5. So the oxidation number of nitrogen is +5. Okay, so this is how you will solve. You should know the simple, algebraic or the mathematical functions. All right, identify what is being oxidized and what is being reduced. So we are going to assign the oxidation numbers. Oxidation number of carbon, this is in a free state. So free state means that the oxidation number is equal to 0. Okay, free state oxidation number is 0. Carbon, let's put it here on top, oxidation numbers on the top. This is the diatomic. In diatomics, the oxidation number of this one also is 0. Okay, so let's put it in a different color. So these are the oxidation number of this, and then the oxidation number of oxygen, 0. Okay, now what do we have here? This is the free state, diatomic state we have identified. Now for carbon, let's say for carbon we don't know, so the x plus oxygen is, there are 2 oxygens, each is -2, and this is a neutral molecule. Okay, so x minus 4 is equal to 0, or X is equal to positive 4. So for carbon is plus 4 and oxygen is minus 2. Okay, so that is still, you know, the oxidation numbers. I have written them on the top like that and like that, so you can see them. All right, now comes the, put them on one side and see. So carbon has gone from 0 oxidation state to 4. Carbon has gone from 0 to 4 oxidation, positive 4, right? Positive 4. And oxygen O2 has moved from 0 to, like, 2 of the oxygens, and both of them have got the -2 charge. So basically from 0 to -2. Okay, so what is oxidized and what is reduced? So that when we move from a neutral state to a positive state, what happens? This is oxidation. So carbon got oxidized and oxygen got reduced. So keep this in mind, that increase in the oxidation number from negative to 0 to positive is oxidation, is oxidized. From reduction is moving from a positive to 0 to negative reduction. So this is acting as an oxidizing agent. This is acting as a reducing agent. And this is acting as an oxidizing agent. Okay, reducing and the oxidizing agent, if that's the question, but basically that's what you do. Okay, next is write a chemical equation for the synthesis of silver bromide. So how will you write this one? Silver bromide is just basically, you can backtrack and you can write on silver reacting with bromine, Br2, and that gives you AgBr. Okay, the rest is balancing. So there is 2 bromines on one side. So 2 bromines now balances that. That 2 applies to silver and 2 applies to bromine. But that if you put 2 here, that will balance the silver also. So 2 silvers, 2 bromines on either side. Okay, write a chemical equation for the synthesis of carbonic acid. How is carbonic acid formed? Carbonic acid is basically H2O plus CO2. Okay, now these are valid molecules. Water is valid, like it's known, it's stable molecule, and carbon dioxide also is known and stable. So here you see this is going to give you H2CO3. So just now we covered carbonic acid. So here you see what you have, these 3 oxygens, and you have 1 carbon, and you have 2 hydrogens. So it's all balanced. Okay, next is write a chemical equation for the decomposition. Now this is a decomposition reaction in which Al2O3 is like heated at such a, decomposition is, you know, basically AB breaking up into its 2 parts, A and B. And again, those should be the stable molecules. So Al2O3 is going to break up into aluminum. As we all know, we have seen it, and oxygen as a gas. Okay, so aluminum is a solid, oxygen is a gas, and this guy is also a solid. Okay, now balancing. So here we see there are 2 aluminums and 3 oxygens. So 3 oxygen on one side and 2 on the other. So we have to look for a common multiple. So if you put 3 here, this makes it 6 oxygens. If you put 2 here, so that makes it 6 oxygens. So oxygens are balanced, but aluminum is now 4 on one side. So if you put 2 here, that balances the aluminum. So here we see that aluminum is 4, and we see also that oxygen is 2 times 6, and so oxygen is 6. So this 2 also applies coming from the oxygen. So 6 oxygens. Okay, so let me write this down. So there are 4 aluminums, there are 6 oxygens, there are 4 aluminums, and there are 6 oxygens. So remember that this 2 applies to aluminum, tries to aluminum and oxygen. This 4 applies to aluminum. This 3 applies to oxygen. Okay. 2 applies to aluminum and 3 applies to oxygen. Okay. This 2 applies to oxygen. So that's balancing. Now, next is the Ag2S. Ag2S, how is this going to break up? So this breaks up into, as far as I understand, Ag2S breaks up into silver, Ag plus sulfur. Okay, and the rest is balancing. So 2 and 2. So 2 silvers and 1 sulfur. Okay, so that's balanced. Okay, now this is also sulfur. As sulfur is also solid, silver is also solid. Oh, sorry, this is solid. Solid. Okay, now write the chemical equation for a single replacement reaction. Now for a single replacement reaction, we have here this activity series in your handout. Okay, and this activity series is basically, one second, I'm trying to look for it. Right here. Okay, so that's the activity series. And we discussed this in the lecture. The elements that are on the top are going to displace the elements that are in the bottom from their bonded state. That's one piece. Second thing is when they react, these are also showing the intensity of the reactions with water, with hot water, with steam, with acids, with concentrated acids, and so forth. And to release hydrogen. Now, where is the hydrogen? Where is the hydrogen here? The hydrogen is going to come between lead and copper. Okay, so between lead and copper, you're going to place the hydrogen. And so which means that lead will react with the acid and release hydrogen, but copper will not react with the acid and release hydrogen. Similarly, all these elements that are below copper, that's mercury, that's silver, that's the platinum, right? Gold. So these guys will not react with the acids. They do not react with the acids. They will not release hydrogen gas. But anything that is above copper, tin, lead, nickel, iron, right? Iron, all of them are going to react with the acids and with water to some extent. So for example, the ones that are higher up, potassium, sodium, calcium, these guys are going to react with water. Potassium and sodium react violently with water, but calcium also reacts slowly with cold water. Okay, but magnesium reacts with steam, hot water, and then it also reacts violently or strongly with acids. So aluminum, zinc, chromium, all of them react with the acids. Similarly, iron, nickel, tin, and lead, these are going to react with acids of very high concentration, and then they're going to release the hydrogen gas. But the copper, mercury, silver, platinum, and gold will not react with the acids. So that's the activity series. Now we see here zinc and lead nitrate. So will zinc break the bond of lead nitrate or not? So let's look at again in the activity series, where is zinc and where is lead? So zinc, if you can see zinc right here is the zinc above chromium, and lead. So right here. So zinc is above and lead is below. So when zinc is above, that means zinc will break the bonds of lead with polyatomic ions or nonmetals. But lead will not be able to break the bonds of zinc. So that's the thing. From top to bottom, it will happen. So zinc is above lead. So let's do this. So zinc, so this reaction is working because zinc is above lead. So therefore, this reaction will work. So here, what is going to, so write down the symbol. So zinc is Zn, okay, acting as a solid, plus lead 2 nitrate. So this is PbNO3 whole twice. So how did I get that? This 2 means lead is in +2 state. And how do you, where is that lead to +2 state here? Okay, so okay, let me just show you. So this is lead +2 state, and you have nitrate, NO3 -1. Nitrate is always -1, but lead. So when you crisscross, that's the formula you get. Okay, now comes the zinc. So what has zinc done? Zinc has basically, broken this bond, and it combines with nitrate, and it releases the lead. it releases the lead. It breaks the lead free. So what is formed here? In this case, then you will see zinc combining. Now remember that zinc is in +2 state. There's a transition element. All D block elements will have +2 charge, and they can have more type of positive charges also. But all of them will have, if you do not know, or if you don't see zinc in the other table, which is the table I have in the handout for, I have it. I mean, once you keep working and then it kind of sticks to your memory. But for now, I just want to show you where are those tables. So these are, of course, all the polyatomic ions, which you need to recognize and memorize. Okay, that's one piece. The second thing is solubility tables. You need to recognize and, memorize. And then comes these ones right here. This is on table 6.5. These are the metals that form more than one type of positive ions. Okay, so here, what do you see? You see these tables. You see these tables right here, these tables, and these tables have the list of all these elements that are, transition and post-transition elements that can form more than one type of positive charges. And as you can, zinc is not here. So zinc will be +2 charge. Okay, so zinc is +2 charge. So here, when zinc combines with the nitrate, NO3 -1. So what happens here? Crisscross, right? So this becomes ZnNO3 whole twice. Remember that crisscross from the nomenclature. So refer to that, refer to the nomenclature if you are still, rusty on the nomenclature, but this is what is going to be formed, and lead is going to be released free as a solid. Zinc nitrate, aqueous, soluble in water. So this reaction will occur. Okay, clear? So this is the equation for a single displacement. Next is balancing. So there are 2 nitrates on both the sides, and there's zinc and lead. So this is all balanced. Next, look at iron with copper sulfate. So here, once again, refer to the activity series, and here you will see that iron is, where is it? Here. So you see iron is above copper in the activity series. In the activity series, iron is above copper, right? So when iron is above copper, what happens? Iron will break the bond of copper in its bonded state, but copper will not break the bonds of iron, nickel, tin, lead. But nickel, tin, lead will break the bonds of copper. So all of them. So here we have iron with copper sulfate. Now here's something, copper and sulfate. Okay, sulfate, charge on sulfate, you should know, is -2. What is the charge on copper? Copper is +2. So that's how it becomes copper sulfate, because +2 -2 cancel out. And what do you have here? Iron. Okay, iron can have +2 and +3, but just for the sake of convenience, let's do this. Iron will make iron +2 charge. Okay, and here you have sulfate with -4, -2 charge. So iron is going to break the bonds of copper and sulfate. It will combine with sulfate, and copper is going to be released. Okay, so in that case, iron and copper will combine. Okay, they will mix. So what are they going to form then? Here we will have the, so this would be copper, so this is iron, FeSO4. And this is all sulfates are soluble in water. So this is going to be aqueous, plus you will have copper released as a solid. Okay, and why is this reaction working? Because iron is above copper in the activity series. Clear? Next is write the complete balanced equation for the double displacement reactions. Now in this case, outer, outer, inner, inner. So you need to recognize the polyatomic ions, okay, and the metals and the non-metals, right? And you should know the charges. So first thing is, what is happening here is that ammonium is going to combine with the nitrate. Okay, these two are going to mix, and then barium and sulfate are going to mix. Now, the next thing is that it's very important you know the charges. So let's do this here. Ammonium, NH4, will have +1 charge, but there are 2 ammoniums, okay, in this. And then you have sulfate. Sulfate is -2 charge. Okay, there's only one sulfate. So that's one piece. Next is barium. Remember, if you are not sure, you can also check, look at this, thing. And if you're not sure, these also are these numbers. Okay, and here, barium. So there are 2 bariums. There is 1 barium, but that barium has a +2 charge. Barium is in group 2A, right? That also can give you a clue. But the other clue, as I said, in the formula itself. So that 2 subscript you see is this thing. Okay, so so this 2 is this sulfate has a -2 charge, which is which is showing as a subscript, and that subscript translates into the so actually that translates into sorry, here, right? Okay, now we have barium +2 and nitrates are NO3 -1 always, but this also means this 2 nitrates. Okay, so this piece is that. So the 2 explains this relationship of the charges and the subscripts. Okay, so that's something you need to know. Now we are going to have this becomes BaSO4. Why does it become BaSO4? Because Ba is bringing +2 charge and sulfate is bringing -2 charge. So they cancel each other out. So this becomes BaSO4. Okay, next is NH4NO3. NH4NO3. Now what happened to the subscripts here? So this is what it is. So here you have NH4. NH4 has +1 charge, and nitrate NO3 has -1 charge. So this becomes equal to NH4NO3. Let me move this here. So this becomes NH4NO3. Okay, so that now the rest is balancing. Now we have 2 ammoniums on one side and we have 1 ammonium on the other side, right? So you're going to put 2 here. So this 2 changes the nitrate also, but then there are 2 nitrates on one side. So that 2 once again is this, the 2 ammoniums and 2 nitrates. This 2 applies to ammonium as a whole, and it applies to nitrate as a whole. So there are 2 nitrates on the reactant side, 2 nitrates on the product side, 2 ammoniums on the reactant side, 2 ammoniums on the product side. There's 1 barium and 1 sulfate. Okay, now since it's a double displacement reaction, now let me write this here again, NH4 whole twice SO4, okay, plus BaNO3 whole twice, and this gives you BaSO4 plus 2NH4NO3. Okay, now here what do you see? In this case, we will see that the complete and balanced for double display. Okay, so here we will see, in this case, let's write down the solubility. Ammonium sulfate. All sulfates are soluble, with some exceptions, but ammoniums are always going to make things soluble. So aqueous. Barium nitrates. All nitrates are soluble, so they are aqueous. Okay. Then ammonium nitrate. All ammoniums, all nitrates soluble, so this is aqueous. And barium sulfate. What's the deal with barium sulfate? Barium sulfate, all sulfates are soluble except like Castrobar. So this guy is insoluble. Castrobar is calcium, strontium, barium sulfate. These are insoluble. Okay. So the last piece we have is using the activity series, identify if these reactions are going to work or not. So once again, let's refer to the activity series, and we have here FeCl2 with zinc. So FeCl2 iron with zinc. So zinc is above iron. You see that? Zinc is above iron. So zinc will break the bonds of iron, but iron will not break the bonds of zinc. So zinc above iron. So write down here, zinc above iron. So yes, this reaction will work because zinc will break the bonds of iron and chlorine and release it. So here you will see Zn, Cl2 is formed and iron is released free because zinc is above iron, that can do. But gold with nitric acid. So here is another piece. We talked about the displacement of the elements, the ones that are on the top to bottom, but the second thing is we're going to look at the reactivity with water or reactivity with the acids. So here's the gold, right? Gold, it's the lowest in the activity series, does not react with hydrogen ion. Hydrogen ion is what? Hydrogen ions are coming from the acid. So this is the reaction with acid, all this reaction. And whenever it says hydrogen ion, that is the reaction with acid. So here you will see no reaction, no reaction, no reaction, because gold does not react. Gold shows no reaction. No reaction because gold does not react with acids. Okay, so that finishes this. This was a very long, okay, but you know, also so many details had to be covered. All right, thank you for watching.